Okay, it's who is that? Who is that?
Oh, your mobile.
Okay. It's a pleasure to have David Vos fly over the pond to see us. It's exciting. And he is at Cologne. Many of you are familiar. I treat him as a mathematician, basically. It's very
That's
deep,
okay.
deep and intricate knowledge of many things quantum, more than you might expect. I encourage you to sign up and meet with him while he's here. He's here for the whole week. It's a good opportunity. Right now, he'll talk about some non-asymptotic running time analysis of some quantum algorithms. So take it away, David.
Yeah, thanks, Victor, for the invitation. Yeah, good to be here again. I've just remembered, no, last time I was here, I had like small kids who were playing around at the UMD farm, because you guys have a farm on campus. I loved it a lot. And yeah, now these days they don't come with me anymore. And also they are no longer interested in sheep, but just in social media. So I guess, burden of growing up. Good. I want to present some work with a bunch of people. And in particular, it is the PhD student Fabian Henze who did most of the work. And I guess, Richard Kueng, and it's been building up on previous work by him. And yeah, Wiert is a student of Richard, and the other people are classical optimization people. All right, good. Here's the outline. So why this project is very different from the work I've done before. So maybe I talk a bit about the meta aspect of choosing this. Then quantum semi-definite programming via Hamiltonian updates is going to be the technical part of the talk, and some benchmarks in the end. But before I go there, I have a slide about what could have been, and now Victor left the room. Okay, let's see, because I offered him two possible abstracts of recent projects, and yeah, option one is the grown-up option is what I'm talking about now, about quantum complexity and industry and actual applications, what all the people with money care about. And option two is some old school 2005 style multipartite entanglement paper that we recently did. And then Victor and me decided we should do the grown-up option. And yeah, if you are interested about unapologetically non-applicable, absolutely maximally entangled states constructions, you know where to find me, and we can chat about that. Okay, good. So back to why I will talk about what I'm talking about. And the starting point is that I don't know whether you've realized it or not, but there's a lot of hype at the moment about quantum computation. No? So this is a copy from a McKinsey website that I copied not so long ago. It says quantum computing just might save the planet. No, and that's maybe the kind of discourse that is not atypical if you talk to practitioners or maybe industry people who now learned that quantum, it's going to be the next big breakthrough. And so, yeah, one thing I had to learn in my country now, I guess it's the same here, that increasingly companies come to me and they want to write grant proposals together where they explore quantum algorithms for their business cases. And here's a typical passage from one of these grant proposals, which the industry partners will write, and then they say, we will demonstrate how quantum algorithms will revolutionize our business processes. No, I mean, that's not literally, but close to what I've read. So then before we send off the grant proposal, I edit it. And after I've edited it, it reads, can you read this actually? Yeah, read it out. So we will explore the parameter regime in which quantum algorithms have the potential to revolutionize our business processes. And that's, of course, they will thank me later come reporting time, because when inevitably we find that they were overly optimistic, I can still go to the grant manager and, have fulfilled my project obligations. Okay, so yeah, so this talk is about what happened when after this was written, when some companies came to us, and right, and so what are the kind of problems they want to solve? Companies don't actually want to break RSA, and they don't actually want to do Hamiltonian simulation. So when they think about difficult computation problems, often one thing they have in mind are combinatorial optimization problems. How to allocate the machines they have with the with the task they have to perform in their factory, for example. And all right, and so that's what they like. And so a question, of course, is quantum actually a good fit for this? And how would we know? Yeah, and I don't know, I guess many of you have opinions on that. I'd be happy to chat. Here are some thoughts on whether quantum algorithms are good for that. So one is right. So these problems, like I don't know, for example, the traveling salesperson problem here, finding the shortest route to a number of points, archetypical example, they're typically NP hard. So there will be no general efficient quantum algorithm, or it's extremely unlikely. So there will be no short type breakthrough here. There are promising heuristics or not so promising, depending on whom you ask. I don't know, QAA would be, what the companies always come to me because they've read it in the literature that this can solve all their problems in principle. But it's very, very difficult to assess how they actually perform on real world problems. It's because, these are heuristics, so you can't prove a theorem about them. So the way heuristics are usually being assessed in classical computer science is that you just have big benchmarks where people come together and benchmark the various algorithms against each other, but we don't have the large scale hardware on the quantum side to make this possible. So we really don't know whether these algorithms, these heuristics will keep their promise or not. Right. Also, maybe one could prove something negative, and show that something can't work on a quantum computer, but that's also very difficult because humanity seems to be not very good at proving lower bounds on computational hardness. So it's a bit unclear whether quantum algorithms are a good fit. Whether quantum combinatorial optimization and quantum algorithms fit together, and if they do, how would we know now? It's very unclear. So I come back to my edited passage. We will explore the parameter regime in which quantum algorithms have the potential, and it seems like maybe even that is unrealistic because we don't have the means actually to decide that. Okay, so these were my slides until this morning, but then I was jet lagged, and so in the hotel I got up at 5 a.m. and so what I do, of course, I read the output of the local group, and then I found this nice paper on the arXiv, including one Mr. Childs. And right, and here I just copied a paragraph where he basically says, or something very close to what I said. There's a lot of uncertainty, he says. Beyond crypto analysis, there are hints and ideas to explore, but because we do not have large-scale quantum computers to try things out, we have to rely on proofs to understand the performance. Okay, that definitely limits our understanding. And so I think there's two messages I want to get across. On the object level, I tell you about the one algorithm we looked at, but maybe what was more interesting for me to learn this project is how to even approach this class of problems. How do we even gain understanding of the real world performance of quantum algorithms if we are lacking the big hardware to try them out, and if we might not be able to prove that they work. And I think I'm a bit, so he says we only have proofs. I think I want to go a bit beyond it. I think there's ways of understanding the performance that might not be quite rigorous, but I think is meaningful. Okay, but it's really about how to navigate the situation. Okay. All right, so then we, against this backdrop, we went into brainstorming mode. What kind of project could we find that does not just reduce to running, a small scale QAA simulation on a GPU cluster and then drawing breathless conclusions from a single data point. So we wanted to do something that has a bit more of a rigorous underpinning, but it's probably also not realistic to wait for a problem that you can actually analyze in full detail the performance of. And so we came to, we found one of, a project which I think worked. And in order to explain to you what that was, I have to go through a number of technical background slides, and it starts with quantum semi-definite programming. Okay. There's the first time I'm giving this talk, so I didn't have sufficient time to put nicer pictures, so I will reuse this one picture from the paper over and over and over again. And I don't know, maybe later if I give it more often, it's going to be more colorful then. Okay, so what is semi-definite programming? A semi-definite program optimizes a linear function over the set of positive semi-definite matrices subject to linear constraints. This is the general form. You're optimizing over X is semi-definite. some linear function subject to linear constraints. There's the unfortunate situation that I will be using the abbreviations SDP for semi-definite programming and PSD for positive semi-definite. They are very similar, and in fact, the S and the D mean the same, but the P means something different in either. So I don't know. You gotta get used to that. All right. So what do we know about semi-definite programming? Not quantum, actually, just classical. So it is classically efficient. It's an algorithm that you can run in polynomial time on a quantum computer, but it's efficient in the sense of classical computer science. So there's a polytime algorithm. In fact, there are different algorithms, right, that scale in maybe the problem size n and the precision mu you want to achieve, and there's a trade-off. Here you got a very bad scaling in the problem size, but an excellent scaling in the precision. For these other class of algorithms, it's the other way around. But in reality, they are often difficult to perform. Like for problem sizes you would like to do them, it's often difficult to do it. Often you are limited by memory. And so people, classical people who do this will tell you that these are challenging algorithms and they would usually like to push further than they can actually do on their hardware. And so there was a big class of ideas by Brandão and Swor in 2016. So, not even 10 years ago. And very roughly, I'm going to explain one of these schemes in detail later, but very roughly, the idea is that quantum computers, they can natively represent very large PSD matrices, namely as quantum states. And so maybe one can build an algorithm around this representation. And that turned out to be at least a very fruitful theoretical field. So let's look a bit closer, and later, as I said, I will explain one of them in detail. So here's the basic idea. So you parameterize the PSD matrix actually by specifying a Hamiltonian, and you would convert them by computing a matrix exponential. At least that's what you would do on a classical computer. In the quantum version, you would take a quantum description of the Hamiltonian and turn it into a physical realization of the PSD state using a Gibbs sampler. And then you have somehow like a physical representation of this matrix, and you can now start to measure the objective function or measure the constraints, which are all linear functions, hence given by physical observables. And you can just estimate them by literally performing measurements on the states and collecting statistics. Okay, and so there's a good and a bad aspect to this strategy. The good is that the matrix size does not actually enter directly, right? Because you're not writing out the matrix elements. They're just held they just represent the state. So only the complexity of the Gibbs sampling that enters. So if you have a very big matrix for which you can efficiently prepare a Gibbs state, then this would be fine. That's good. The bad is that the data is stored in a kind of analog way, right? So there is, you don't write out the coefficients of the PSD matrix directly, but again, it's a quantum state. And so you can't just read out a matrix element. You have to statistically estimate what any linear function is by performing physical experiments. And of course, we all know the bane of the quantitative social sciences is that statistics converges very slowly, and we need very big sample size to get anything done. So that's very expensive. Also, the algorithm is absolutely not what some people call, NISQ these days. It uses difficult to realize primitives. For example, in many models, you would have large-scale quantum RAM in order to run these algorithms. Okay. So like from this very high-level description, what one might expect is that these quantum semi-definite programming algorithms have a good scaling in the dimension of the problem, but a bad scaling in the precision.
What do you need quantum RAM for?
Okay, so the question is, how is the input specified? Yeah, and I mean, this depends. It's part of the small print, but one way is to have the Hamiltonian, or some representation of the Hamiltonian in quantum RAM as an input for the Gibbs sampler. There's one, presentation issue. There is the precision here is called mu. It was called mu before. Later you will see the letter epsilon, and yet later you will see the letter delta. They all measure precision in some sense. In the paper, they all refer to kind of slightly different precisions, but in the talk, I will not keep them apart. So whenever you see a Greek letter, that's some kind of precision parameter. Yeah.
So the Hamiltonian, if you have to specify the Hamiltonian, it's also exponentially n. So
Aha, okay, so right, in this game, n is not the number of qubits, but n is the dimension here. Yeah, that's right. Yeah. I mean, of course, ideally you would have to, there might be some Hamiltonians which are like physical Hamiltonians, right? Where the complexity of specifying h is logarithmic in the dimension. This is not usually the scenario being considered here. But of course, if you have it, then this is what I refer to here. So then the actual dimension of the system doesn't really enter, and the Gibbs sampling could be very efficient. So that might be a good situation. Okay. Aha, in fact, what do you mean by unfavorable scaling in the precision? Here's the abstract of the original paper, and you can see now, don't have to read it in detail, but you can see they prominently advertise the scaling of the algorithm and the problem size, the number of constraints, the sparsity, and then the precision is here at 1 on delta, and there's a poly in front of it, and many others have a log, but this doesn't have a log. So it's some polynomial, and they didn't even write out the exponent for reasons you will see in a second why they didn't write it out. So it tends to be very bad in the precision. Okay, good. So that was technical background number 1. Now comes technical background number 2. We'll talk about QUBO's SDP relaxations and Römer-Williamson method. So this gentleman, he's at MIT, but he's a Belgian from the Flemish-speaking part, and I had a Dutch PhD student, and he told me to pronounce the name as Römans. So that may or may not be correct or recognizable to you, but when I say Römans, I try to be correct. Okay, so let's talk about what Römans and Williamson did. Okay, so let's now actually take one specific optimization problem, combinatorial optimization problem, and stick with it. And the favorite one for quantum information purposes, somehow it fits many of our constructions. These are QUBOs or quadratic unconstrained binary optimization problems, where you want to solve the following problem. So you maximize a quadratic function. C is the cost matrix that will occur many times in the following. X is a vector, and the elements of the vector are binary variables. So they are, each component is plus minus 1 valued. And yeah, you want to optimize this quadratic function over the set of vectors that are plus minus 1 valued. It's NP complete problem. Okay, so let's rewrite this a little bit and see what we can do. Now, rather, that's the one way where, you know, this talk connects to what we were talking about 10 years ago. You can lift this problem from one that is quadratic in the vectors to one that is linear in the outer products, and that will be the basis of the quantum mechanical treatment. Okay, so the objective function here, you can write it, it's actually printed on the right-hand side as a trace of the cost function with a matrix capital X, where capital X is, in this classical context, the outer product, which of course in quantum mechanics we write as a cat graph. Right, I mean, obviously these are the same things. And so because it's now linear, you can replace this optimization as an optimization over the convex hull of all these outer products. Right, and then it becomes maybe in this formulation a bit surprising why this is a computationally difficult problem, because now we are optimizing a linear function over a convex polytope. It's a polytope because there's finitely many vectors of this form, and they form the vertices. You take the convex hull, you get a polytope, you optimize a linear function over polytope. That sounds like a linear program, which is known to be efficiently solvable. And the caveat is that the hardness stems from the fact that this polytope is very difficult to describe. So there is no polynomial time membership algorithm that would tell you that you're actually inside this polytope. Yeah, so it somehow feels like it's very close to being efficient, but not quite, because yeah, it's the complex polytope that messes it up. And then there's an obvious idea, namely, maybe you can relax the problem a bit and replace this difficult to describe polytope with another convex body that is slightly larger, but maybe not too much larger, but easy to describe. Yeah, so you want to maybe, all right, it mostly doesn't matter that you can't see the lower part, but here there's a picture of this tetrahedron with the faces blown a bit out. Yeah, and that actually works. And yeah, let's describe here. Okay, so let's look at these outer products, X transpose X, right? The capital matrix X. So that is obviously a positive semi-definite matrix, right? Because it's an outer product. of the same vector with a vector with itself. And it also has obviously the property that the main diagonal elements are equal to 1. Why? Because the vectors I'm taking the outer products of have ±1 valued components. Okay, and so the first bit of this relaxation is to just keep these two properties, namely PSDness and having all ones on the main diagonal, and forget all the other conditions that are also true on this polytope. And this, all right, this gives me now an outer approximation by a semi-definite program, because I can now replace the problem I started with a maximization over semi-definite matrices where the diagonal is all ones, and then I express the objective function in the same way. Okay, and so because I've only dropped constraints, I made the domain over which I optimize bigger, so the maximization could give you a slightly larger value. Yeah, but as you will see in a second, it's actually not that much larger. So it's pretty good. And this looks like something very close to a quantum experiment. No, in quantum, you wouldn't say X, but you would write rho, and rho is just a renormalized version where I divide by n so that the trace of this thing becomes 1, where it's now obviously n. Okay. All right, so this gives an upper bound to the optimal value, but it even gets better. You don't just get an upper bound. There is this trick due to Röhrmann and Williamson, or at least they analyze the performance. Namely, if you have such an SDP solution, yeah, it gives you a matrix capital X that is not actually rank 1, so you can't naively find a ±1 valued vector there, but you can construct one with what is called a randomized rounding procedure. I walk you through it quickly, but it doesn't matter to understand the detail here. So you take, if let's say rho is the solution of this, or I've switched notation now from capital X to lowercase rho, it's the same thing. Yeah, you take the solution that comes out of the SDP relaxation, you take the matrix square root, and you sample a Gaussian vector, you act with the square root on the Gaussian vector, and then you take the sign of the resulting vector. Now you got a ±1 valued vector that is somehow constructed from the SDP approximation. And what made Röhrmann and Williamson famous is that in expectation, the solutions you get this way from randomized rounding are within a dimension-independent factor of the optimal value. And these factors tend to be very good. Yeah? So it's actually a pretty good way of getting approximate solutions, not just upper bounds, but also approximate solutions to an NP-hard problem. Yeah.
This sounds amazing. What's the idea of proof?
That's the idea of proving. It's not difficult to prove. Okay, so I have some more pointers here, but we can also talk about it. I think, I can probably do it in half an hour or something. It's not difficult to do. Yeah, it's really, so this picture up here is, if you study that for half an hour, you can basically find the proof. It's not difficult. Okay, so there's, by the way, it's a conjecture. It's related to the unique games conjecture that for many NP-hard problems, this actually gives the best polytime approximation that is doable. If you want to get any better, you get into conflict with NP-hardness. That's not proven. It's not even equivalent to P, not equal to NP, but I think it's widely believed. So these are very good. And these techniques has many applications. Like, I don't know, there's like this Grothendieck inequality if you care about tensor norms, or to upper bounds on violations of two-party, two-outcome Bell inequalities. They come from the same kind of argument, or the spherical model of statistical mechanics. So these methods are well known and used in many places. Okay. Right, now let's combine these two things and talk about quantum SDPs for QUBOs. So recall, what's our mission actually? So the problem is the companies want to know about quantum algorithms for NP-hard problems, but the performance of heuristics is difficult to assess. But now we might be onto something that I can actually work on and look into the mirror the next morning, and that might actually be of interest to these people. Okay, so these SDP methods, they give the best possible tractable approximation, so they're pretty good. Their performance is well understood analytically. It's a bit of geometry and semi-definite matrices. There is quantum, yeah, so now the problem is if you want to run them on your classical computer, if you have large instances, they're very difficult to run, but the quantum implementations might get around this. And also they are very bad, the quantum algorithms are very bad in the precision, but that might not be so super bad because, for example, we have this rounding step in the end, which anyway means the individual precision doesn't matter so much. So it seems like it might be a good fit. Okay, so we can hope now for a bullshit-free, non-asymptotic, well-justified quantum advantage for a relevant problem class. As a non-native speaker visitor to your country, you have to tell me whether this is an appropriate thing to say in the talk. Okay, good. So now I can link back to the title of my talk. That sounds like a real good idea, no? Somebody should work on that.
So for the third bullet, you're hoping for polynomial improvement?
Right, yes, okay, yeah, we'll hope, yes, I'll show you on the next slide, actually. Because not only does it sound like a good idea, it also sounded to a good idea to other people, because there's actually prior art. And so basically this project builds on this paper here by Fernando, Richard, and Daniel from 2019, I think, where they did exactly that. And so you can say, what's left to be done for me? They showed that you can combine these things and you can have quantum SDP approximations for QUBOs, but it's very much in the proof of principle state, because here's the result they have. And so they have a quantum version and a classical version. So the algorithm works, on both architectures. And the quantum version has a running time that scales in the problem size with an exponent that's basically a square root of the classical one. It's basically a square root advantage. Here you find a precision statement. Before, like in Fernando's first paper, they didn't even give the exponent. Here they give it, and it's 28 plus lowercase over 1. So it's very much proof of principle. And yeah, in the classical version, the exponents are a bit better, but also pretty bad. And so that's good now. We got ourselves a project, because now we can tell our partners from industry, okay, so you think, all the literature that's out there on how good quantum algorithms are, this applies to your problem. So let's just, take a published algorithm, one that's easy to analyze, or easier maybe than the heuristics, where one of the authors is on our team, namely Richard Kueng, and work it out and find the non-asymptotic details. Right. Okay, so here's our plan now. So we start, at this theorem 1 of their paper. Okay. All right, and because we have this, we have only like a square root advantage in n, so it's not very much to work with, but also it's kind of counteracted by the very bad scaling in the precision. So there will be a quantum advantage for very large scale projects, for very large scale problems, but it will probably manifest only for very big values of n. And so the question is now, the question that we ask ourselves is now, how large? So in a non-asymptotic way, can we make some reasonable statement about when the slower growing quantum complexity line will cross the classical one? Sorry.
So, you see above S is the column sparsity. So it's, I guess we didn't really talk about it in the 2 background sections. How should I think of S here?
Yeah, it is indeed. Yeah, you're right. It is indeed the sparsity of H. Yeah. Yeah, column or row sparsity, it's symmetric matrices.
And how is that related to capital C?
Yeah, so it's essentially C. We'll see it in a second. Yeah, the Hamiltonian will be built out of C and some other kind of constraints. I'll show in a second. But oh no, it's actually literally. Not just essentially, but literally that it says here. All right, okay. So we start with an n by n symmetric coast matrix with column sparsity S. Right, okay. And yeah, so you can also, if you want to avoid complexity, multiply n and s together, and then you still, yeah, you have a behavior here that's essentially, as I said before, the square root of the classical one, a bit less actually. Sorry, did this answer your question or?
I'm fine, thanks.
Is that related to matrix vector product, which instead of being full matrix being sparse?
Yeah, maybe in the classical implementations where I'm not super sure how they actually work, but in the quantum one, it is this Gibbs sampler. So the subroutine that takes the problem description as an input and basically does a quantum version of computing the matrix exponential. This is faster for lower sparsity. Yeah, so it's, yeah, if you want to think about it from a classical background, it's like the quantum matrix exponential algorithm that is sensitive to the sparsity. So I'll explain to you how the algorithm works in more detail on the next slides, except for the Gibbs sampling, which I will outsource as a subroutine. So I'll talk about that. Yeah. Good. Any more comments or questions?
Oh, sorry.
Yeah.
Call this analysis non-asymptotic.
No, that's not yet non-asymptotic. Oh, sorry. Yeah, the title of the slide is what we want to do, but it wasn't done yet. Yeah, of course. Sorry. It's yeah, okay, I gotta change the title. Yeah, not yet non-asymptotic analysis. So our question is, how large does n have to be before the square root advantage here actually means you got an actual advantage? Yeah. Okay. All right, then I will, okay, now, okay, before I actually go into the details. So what's now the high-level work program? So we hire this PhD student and we said, okay, why don't you work this out? And this took like more than a year of the PhD students. In fact, it was the second problem. The first one failed. That can happen in science. And I wanted to give him like an easy project to complete. And then it also took more than a year. Yeah, I think in the middle, he was a bit unhappy, but now he's graduated. It's fine. Yeah, sorry, that can happen. No, okay, good. So what did we have to do? So first, we could have just, taken the Brandão Kueng França algorithm and asked the student to code it up and to benchmark it. But that wouldn't be fair or meaningful because obviously, and Richard would confirm it to us, they stopped the moment they obtained an asymptotic proof of principle result. Of course, they didn't try to optimize it. There were many choices where once scaling was polynomial, they stopped and moved on. So it would be like, kind of comparing other methods against a strawman if we wouldn't, if we would just take it as it was spelled out. So step one of the program is we had to optimize their algorithm, which goes by the name of Hamiltonian updates for a reason that will be obvious in a second. And then only step two would be to benchmark and compare. So as you can kind of anticipate, the end result will be that this doesn't work at all for any realistic problem size at all. So it's, but before we could comfortably make a negative statement about this algorithm, we had to kind of prop it up the best way we could. Yeah. So I don't know, you prop up your opponent to punch them in the face. That's not how we thought about it, but that's what happened. Okay, so now I will explain to you, there were some questions already in this direction, how this Hamiltonian update thing actually works. And these are, unfortunately, this is like 1 of 6. It's going to be 6 slides. None of them is very technical, but you can actually understand how this algorithm works. So I think, that's a few minutes well spent. Okay, so here's, to remind you, that's the problem we want to solve. Yeah, okay, let me make this also clear. I kind of should have said it maybe more clearly. We are not trying to solve the actual NP-hard problem to optimality. We only want to have a better algorithm for this SDP relaxation. So this, this would make us already happy. Okay, and so that's the SDP relaxation. Okay, and so first thing is for technical purposes, we convert the maximization problem into a feasibility problem. Yeah, that's actually very easy to do. So we want to find, we choose an candidate optimal value of gamma, and we want to find, answer the binary question: is the objective value bigger or smaller than gamma? And if you can do it for all gamma, then using a binary search on the interval of possible solutions, if you can solve the feasibility problem, you can also solve the optimization problem with only logarithmic overhead. So that's a standard reduction, and it makes things a little bit easier. And of course, in reality, we can't even solve the exact feasibility problem, but there will be a relaxed feasibility problem where some precision parameter epsilon. Right. I mean, certainly on quantum hardware, because you have to use statistics to measure all the values. So if you can't read it, just the same as above, but everything, every 0 is replaced by an epsilon, except for the equal to 1 here, because quantum mechanics is pretty good at ensuring that trace rho is equal to 1. Okay, fine. So just moving forward, we will look at the sequence of feasibility problems parameterized by a candidate value gamma for the optimal value and some precision epsilon. Okay. So now technical ingredient number 2, that comes back to your question before. We use a parameterization of the positive semi-definite matrices in terms of Hamiltonians, right? And so, that's the obvious way of going back to the semi-definite picture. which of course is a Gibbs state in quantum language. All right, so now we are actually rewriting this optimization problem as a problem in H. It's the same as before, but now the variable is a symmetric matrix. Okay, we also initialize at H equal to 0, which means we initialize at the maximally mixed state, and then we do a sequence of updates to try to move closer to an optimizer. Okay, and so this is like where Hamiltonian updates gets its name from. Yeah, so it's now a iterative algorithm where you start somewhere, let's see here in the middle of the block sphere at the maximally mixed state, and then you measure your objective function and you measure your constraints. But now, of course, it's feasibility problem, so there are only constraints. So let's say, yeah, let's look at the cost update. Okay, so there is, you now define an observable PC, which is gamma times identity matrix minus a cost matrix. And so you measure that, and the problem is feasible if you get a negative value here. And we don't require it to be negative, we just require it to be smaller than epsilon for our position parameter. So the geometry of the situation is that the feasible region is here in dark red. Yeah, the observable, which is essentially the cost matrix, shifted by our candidate for the objective value, that defines a hyperplane. And initially, we are on the positive side of the hyperplane, and we want to move into the negative half space of the hyperplane. Okay, and so in order to do this, we take our current iterate, we just measure it, and then probably we get a value that's very positive. So we are far away, and so we have to now change the Hamiltonian, that's the update step, to move toward the feasible region. And so what we do is, if it's infeasible, we update the Hamiltonian by adding the violated constraint times a learning rate lambda. And now from statistical physics, to all the physicists in the room, I don't have to explain why that works, because the StatMech intuition is that if we add a p component to the Hamiltonian, then we having large values of p becomes energetically more expensive. And so in the Gibbs states, you will reduce the expectation value of that. Yeah, like it's quite literal, I don't know, StatMech physics that we're doing here. All right. Yeah.
Where is the value of lambda?
Aha, very good question. So that's yeah, that's the learning rate, so to say. So you don't want to update too much because you have many constraints at the same time. And if you mess with your Hamiltonian too much, you might mess up, you know, good things you had later. And there will be a big question how to choose it well. And in the first paper, they just chose it some fixed size. And one of our big improvements was to make this adaptive. Yeah, it's a good question. We'll come to that. All right, good. Does that make sense? That's basically the algorithm, and then you iterate, yeah. And you iterate, yeah.
But the PC, I mean, this will always just be like a linear combination of one and this constant C matrix.
Yeah, okay. Now you're a bit confused because we only have one constraint, but there is also, maybe I'll answer this question after the next slide, because that's just for the cost constraints, but we had a different type of constraints, namely that every main diagonal element is equal to 1, or 1 on n after I renormalized. Okay, so I alternate between doing cost updates, but also updating the diagonal constraints, right? So this works kind of similarly. So I estimate, and this is actually what's going to be the most important or most costly step in the implementation. I estimate the main diagonal increase by performing computational basis measurements. I see which computational basis elements are bigger than 1 on n and which one are smaller. And then I add another term PD, D for diagonal, penalizing the deviations, right? So if I have a main diagonal element that's too big, yeah, then I would try to make it, yeah, penalize this direction, and if it's too small, I would reduce the penalty on this. And so this I now alternate these two schemes, and so the Hamiltonian I build up will be a linear combination of the cost matrix and these diagonal terms. Right, and this is going to be very expensive because I have to estimate n values, yeah, from measurements. Okay.
Is it a linear combination or actual product of exponential? I suppose it's the non-commute, right?
I'm not super sure I understood. Can you say again?
So the PD and the other one do not commute.
No, they do not commute.
So do you actually take the Hamiltonian level, or you
so as a Hamiltonian, I just add them up, and then this exponentiation is not performed explicitly in the quantum computer because that's what the Gibbs sampler does, but in the classical implementation, yeah, you just add them up and perform a normal classical.
Keep track of Hamiltonian, so to speak.
Yeah, you keep track of Hamiltonians, but the actual functions are all linear in the exponentiated version. Good. So now we come to the big question, like maybe the biggest contribution of the original paper was how to solve the following problem, namely, okay, so now I have a sequence of iterates, and it's a feasibility problem. So if I find at some point a matrix that's feasible, then I win. But what if I never find a matrix that's feasible? At some point, I have to give up and declare the problem to be infeasible. And that is a bit, that now is a non-trivial analysis. How do I do that? And so that's what they that's the main problem, I think, technically, they had to solve. Okay, so it's a bit technical now, and now I will regret that you can't read anything below here. I try to guide you through it. Okay, so let's first assume there is a feasible state, and so we'll derive a condition based on this assumption, and if I fail to see the condition, I know it's infeasible. Yeah, so it's a contrapositive argument. Okay, did you call me a mathematician? A mathematician is somebody who used the word contrapositive. Yes.
I have to start a remark by saying remark. Cool. That's also something.
Okay, yeah, that's right. That's true. Yeah, I try to think of this. Okay, so assume there is a feasible state, rho star. And so the goal is to track the relative entropy distance between my current iterate rho and rho star. So there's an elementary fact, namely that the distance of any state from the maximally mixed state measured in relative entropy is at most ln log n. Yeah, okay, yeah.
How did you choose that order of the arguments of the relative entropy distance?
So why the relative entropy distance?
Why that order of the arguments?
Oh, did I get it the wrong? Did I get it why this order? Okay, it will. I'll maybe again wait for 3 slides, and then I'll expand this definition, and then we can hopefully see. Yeah. But also, there's one way if you put so the target could be pure state, for example, no? If there is actually we want to have like rank 1 axis, no outer products of actual solutions. And so I mean, in order for this to make sense, so the relative entropy becomes infinite, if there's a rank deficient state. In this direction, I think it works. Okay, so I think it wouldn't have worked the other way around. No, you need something with big support on the one side, and everything with rank deficient support must go on the other side. Does that make sense? I don't know.
I thought the full rank state should go on the right,
but there is of course a possibility that I got the order wrong here.
Okay. Not very important at this point.
Yeah, I hope so, because it's definitely possible. In fact, right here it's wrong. It's actually inconsistent. No, the one on n should be on the left-hand side, and there should be a row there. Is that what you meant? Because in this case, you're right. So these two are actually inconsistent. I think this is right, and this is probably wrong. Anyway, I have it expanded on 3 slides down the talk, so then we can look at it. Okay, so now what they prove is, okay, the following is a non-easy lemma in their paper. So if a constraint P is violated by at least epsilon, then the update will decrease the relative entropy distance by something of order epsilon squared, and this coefficient here is known. So we call what I call this Studmak intuition. If you penalize some term, then you will kind of, you will move closer to a feasible point. So this can be actually made precise and quantitative, and relative entropy is chosen because for relative entropy you can prove this quantitative statement. Right. Here is also the learning rate is now suddenly called epsilon. It was lambda before. I apologize. Okay, good. And so now we have this conclusion. So if no solution is found after O of epsilon to the -2 steps, then the problem must be infeasible, because if there were a feasible solution, by the time you would have used up your relative entropy budget, and if you haven't found one by that, then none exists. Okay, so it's a quadratic scaling, which is not great and not terrible, and it was enough for that paper. Okay, then we are almost done. The final thing is rounding. So we have to go back to Römer-Williamson. So, this was the algorithm I claimed is fantastic. So the way it's stated, it only works if the diagonal constraint is exactly fulfilled. And two of our co-authors were classical optimization theoretician, and we asked them, what about Römer-Williamson if the constraints are only approximately fulfilled? And then we didn't hear back from them for 3 months, and then my physics PhD student solved it. Okay, but they had already a proof in their paper, of course, but the student improved it. Okay, so we only enforced that approximately, and so BKF, they generalize it, and we later improved. Though this also hurts a lot because the quality of the solution quite strongly depends on this epsilon. So Römer-Williamson really wants your constraints to be fulfilled exactly. All right, now you got all the things in the bag. So now you kind of know how the algorithm works. And okay, so now our work started to like prop it up and make it better so that if we later conclude that it sucks, at least, we gave it, an honest try. Okay, and so kind of my honor depends on you believing me that we tried everything to really make it work. So by way of proof by authority, I have a long list of bullet points of all the improvements we made that took more than a year of a PhD. And I will go through them, very quickly, not expanding the details. Maybe mainly the purpose of the slide is that you believe me that we didn't knock it down cheaply. So first, your idea, we made the learning rate lambda adaptive. And so you want to have of course, in like iterative algorithms, you want to have a big learning rate so that you don't, move very slowly. But if it's too big, then there's a chance that you undo progress you made in other directions. And there's some kind of technical way what too big means for us. And maybe I'll explain later, or maybe not, if you ask me. Okay, so this made a big difference already. So, the first improvement you would have gotten very easily. Then there was one PhD student, Wiert, and on the team, a student of Richard's, and he started his PhD actually on classical machine learning. So he, of course, knows all the tricks of stochastic gradient descent because, that's what he has been doing his entire life. And he told us you have to add a momentum term. And I had no idea what a momentum term is. And it's somehow apparently in these gradient descent algorithms, you add a component to the update that's proportional to the last update you did. And I asked him, oh, that sounds counterintuitive. Why would you do it? And he said, no idea. Because it's deep learning they're doing, no? And then I was like, that's unlikely to work. And then he implemented it and everything became much faster. I have absolutely no idea. There's no theoretical justification that makes any sense to me, but apparently you got to have a momentum term.
But takes you out of local or something.
Or maybe I should have talked to you, but I don't think, I don't know. But do we have local minimas? We don't have local minimas.
Yeah.
It's all convex. So I have no idea. Like, don't ask me. Okay, good. Then the next thing is the correction of the diagonal terms. I showed you that we look at the sign of, are they bigger than what they should be or smaller? And we made a correction based on this alone. And so we changed it to make the correction proportional to the violation. So if we are far away from where we should be, we penalize this direction harder. Okay. Then we switched from relative entropy tracking to free energy tracking. That's what I'm proud of. And I will tell you a little bit later how that works. Also because it sounds like we're doing physics, no? Yeah, then the bound for the rounding, the approximate Römer-Williamson, this is, what the optimization theoreticians couldn't do and my PhD student could do. And also we did, so these, as a subroutine, we call to a Gibbs sampler, but of course, Gibbs sampling is a very big field and people like Andrew, who works on Hamiltonian simulation, they come up with new algorithms every few years. And it's been a few years since the first paper. And so we updated to the performance parameters of the newer Gibbs samplers. Okay, good. The one thing I want to explain to you a little bit is this free energy tracking. So if you have a job with teaching obligations like me, then the good thing is that you kind of learn the basics of physics. Like in classical mechanics, you can ask me anything, and I'm pretty good at it now because I have to teach it. The only thing is StatMech, we have some experts in StatMech at our department, so I never get to teach StatMech. So I'm very rusty on my free energy stuff. And I had to read like the Feynman lectures for this project. It's a good book I found. Okay, so now you can tell me whether I used the arguments in the right way, but I think now it actually makes sense. So I expand this relative entropy for the case where rho is the exponential of a Hamiltonian h, and then you get this formula where the term here what the StatMech people call the free energy up to a sign. Okay, so we start at the 0 Hamiltonian, and for 0, of course, this is just minus log n. And now it's easy to see that we can reformulate this relative entropy tracking in terms of a free entropy tracking. We start off at minus ln n, and then as the Hamiltonian updates builds up a Hamiltonian, this term increases. And if the problem is feasible, then Hamiltonian updates will have found a solution before it becomes positive. Yeah, it's not difficult to see. I'm running out of time, so I don't show you why. But then, so instead of tracking relative entropy distance, we track the free energy that this Hamiltonian has built up over the course of the algorithm. And then you use the one StatMech formula I still remember from my undergraduate times, namely, if you want to compute expectation values in the Gibbs ensemble, you can get them by taking derivatives with respect to these conjugate variables, or however they call it in StatMech, of the free energy. Okay, and so what this does is this formula that is hopefully known is it links the free energy change to the degree of violation of the constraint. And so if we have a big violation of the constraint, then we can make a big update step and can also account for this step being big in our free energy tracking. So we can much faster conclude that a system is infeasible if it is infeasible. Yeah, so in the original paper, they had a constant there. And now if we see big violations, we know we would have converged faster. And this makes a very big difference in detecting infeasible solutions. Okay, good. So fine, coming to the end of my talk, I will not tell you about all the other improvements, but just believe me, we tried very hard. So now so now we can summarize here and see what we found. So now first, let's see. Right, so here are some asymptotic results, and here are some simulations. So it's a small scale 128 by 128 simulation. And you can see what the various improvements do. So if you have a feasible instance, an infeasible instance, or if you do an entire binary search where you will switch between the two. Right, and so the original had hundreds of thousands of iterations, and adaptive step size gives 2 orders of magnitude improvement. Entropy tracking doesn't matter anything for feasible instances, but for infeasible ones will be important. L2 norm-based PD, that was like the diagonal constraint, taking the degree of violation into account. With momentum, I have no idea. Yeah, okay. And so we go down from 100,000 to 40 or something. For a feasible instance, for an infeasible instance, it's this entropy, or free energy tracking that has, I don't know, 4 orders of magnitude improvements. Bang. So it's very good. Okay, so now you see some in the original algorithm, there are sometimes little daggers in the figures, and if you read the caption of the paper, it means some of these were extrapolated because the original algorithm would have been too costly to run. And now we have dozens or a few hundreds of iterations, so it's much, much better now than it was before. Also, some asymptotic exponents we could argue are much smaller than they were in the first paper. Anyway, so 2 conclusions. The thing got much faster. I will in the final 5 minutes, I will be negative. Let me first say something positive. So after these improvements, I think the classical version might actually now be a usable algorithm. I say might because it was still just one PhD student taking away in Python. Yeah, no, and we didn't compete with CVX or something. But I think it's now. But in the end, whether he used actually CVX or this one, it was at least not worse to use our Hamiltonian updates in the classical version. So I think with some further optimizations, it might be a good idea to use it. All right, and now for the quantum advantage. Now we want to find if we now turn to the quantum problem, at what problem size could we see an advantage? And now we come back to the Enroll-Childs discussion at the very beginning. How do we actually know that? Because we probably can't prove a theorem. So we have to argue a bit more, I hope convincingly, but it's not going to be a theorem now. Okay, so what did we do? So we ran the algorithm for random problem instances up to what the student's laptop could handle. We logged every time we would call out to a quantum subroutine like Gibbs sampling, we logged all the relevant parameters that go into the performance of a Gibbs sampler. And so we knew how fast a quantum computer would have been had we called it. Then we estimated the number of quantum gates that a quantum implementation would have required based on reading just state-of-the-art implementations. Yeah, so that went painstakingly. It's very painstaking because these Gibbs samplers are now very sophisticated to these papers and counted gates. And in this, that's an inexact science because this is now not an asymptotic result. So it's depending on the implementation of the architecture. And so whenever there was any kind of question, we've been extremely generous to the quantum version. So we only, for example, counted 2-qubit gates. We didn't count single-qubit gates. We assumed no error correction overhead. You got the perfect quantum hardware. We only counted the quantum cost of the diagonal estimation, and all the other things we just gave the quantum computer for free. Like when I said there are parameters that go into the Gibbs sampler, like some kind of condition numbers or spectral information. Sometimes the Gibbs sampler would perform faster if you knew these parameters, but it's not obvious you know them. We just pretended we knew them all. We pretended the Gibbs sampler is exact, even though it only gives approximate solutions. So we, like in every turn, we said, okay, for quantum, and this would be justified a posteriori in 1 second. Okay, so now comes a not so obvious question, and maybe some of you have an opinion on this. How should one compare the results to the classical running time? It's not so obvious because, again, like in complexity theory, everything is asymptotic and well-defined. Here it's a bit not so clear. Here's what we did. And I think it's okay, but you tell me. So we divided the classical running time on a laptop or whatever by the number of quantum gates an implementation would have required. And it's a very, very conservative estimate of the number of quantum gates. And so then we get out of time. And so a quantum computer would have been faster if a necessary condition for this is that the gate time for 2-qubit gates is at least as fast as this quotient, right? Otherwise, if we had a quantum computer, it wouldn't have made any point to use it. Okay, and then we come finally to the following graph that I now have to explain. Okay, so here's the classical computing time. So how long did it take the classical computer to solve the problem? Then here is the gate time for 2-qubit gate that a quantum computer would have had to achieve in order for the quantum implementation to be faster. That's what we could simulate, and these are various extrapolation based on more whatever. These are various extrapolations. Okay, up here is the fastest time of any quantum gate that's ever been reported in the literature, and it's a single qubit gate, not even a 2-qubit gate. And that's a logarithmic axis. So, okay, so in this very naive counting, where at every point in the way we gave all the advantages to quantum, the problem size for which a quantum computer is better is the point where these two lines intersect. Yeah, this line and this line. They will intersect. They have to intersect because there's a provable quantum advantage. Asymptotically, they will intersect. But, oh boy, that will take some time. And this is a logarithmic scale, right? And so I don't even, we put some numbers into the paper, but it's not close. No, it's not close. It's not close. So here's, so there's no realistic regime of quantum advantage that is visible here. It's not a no-go theorem. It's not that we proved that it can't be done, but after 1 year of hard work and trying to make it as good as possible, we just can't see it. It's way out there. I've since learned that in computer science, such algorithms are called galactic. A galactic algorithm is an algorithm that is the best in theory, but where the advantage manifests only at problem instances that are galactic, and they will never be solved in any way. All right. Yeah, there's a little bit, if you really want to be really extra generous to quantum, then there is maybe one caveat, namely the running time of the quantum algorithm is dominated by statistical samplings, and so these could be parallelized in principle. So if you say there's like this, meteor on a collision course with Earth, and we need to like pool all our computational power to, design the interception, mission and we commandeer every quantum computer on planet Earth, like 1 million bad quantum computers, and they could all work in parallel. I mean, of course, in reality, we would all die in this scenario because it would still not work, but at least, you know, the long runtime is parallelizable. So if you want to have like, okay, it's not very convincing. So we just can't find an advantage. Okay, then that's my summary. It's tough to estimate non-asymptotic running times of quantum algorithms. And if you can do it, it's tough to find reachable regimes where quantum advantage manifests, even if it's asymptotically proven. And so, yeah, so, okay, so it sounded like a good idea. I don't know. That's my presentation. Thank you.
Yes, quick question.
So just in the last plot, these dots, they were for different problem realizations or?
Yeah, that's right. I mean, there's a randomness in choosing the problem instance here.